The United States Army has officially designated its next-generation tiltrotor aircraft as the MV-75 Cheyenne II. The naming follows the service's long-standing convention of honoring prominent Native American tribes, placing the platform alongside established helicopters such as the Apache, Chinook, and Lakota. The II designation references the Lockheed AH-56 Cheyenne of the Cold War era, an aircraft that, despite not entering serial production due to developmental challenges, was regarded as one of the most technologically advanced rotorcraft of its time. Looking ahead, the U.S. Army intends to replace a substantial portion of its existing UH-60 Black Hawk fleet with the MV-75 over the coming years, marking a significant transition toward higher speed, longer-range vertical lift capabilities. In this video, Defense Updates analyzes how U.S. Army's new MV-75 Tiltrotor Cheyenne II is shaping up. Before we proceed, a word on NordVPN, which is one of the most trusted and fastest VPN brand that has a no-log policy validated by Deloitte. NordVPN provides a 256-bit encrypted tunnel that protects your privacy and also enables you to access contents that are blocked based on geolocation. Its threat protection system helps you avoid phishing, scams, and malware. NordVPN application is available for all the major platforms as well as browsers. Get an exclusive NordVPN deal with massive saving by going to nordvpn.com/defense or clicking the link in the description. It's risk-free with Nord's 30-day money-back guarantee. The UH-60 Black Hawk has long been regarded as one of the most successful rotary wing platforms ever fielded. Yet its design origins in the early 1970s reflect an operational paradigm that has since evolved significantly. It was conceived for a battle space where missions were conducted relatively close to secure bases and where adversary air defense networks lack the sophistication seen today. Contemporary operational doctrine, by contrast, demands the ability to project force across far greater distances while operating within increasingly contested airspace characterized by advanced integrated air defense systems. Under these conditions, extended range and higher speed are no longer optional performance enhancements, but fundamental operational requirements. Recognizing these constraints, the United States Army had concluded that legacy platforms such as the Black Hawk cannot be adapted sufficiently through incremental upgrades alone, prompting a shift toward a clean sheet replacement strategy. This led to the launch of the Future Long-Range Assault Aircraft (FLRAA) initiative in 2019, aimed at developing a next-generation vertical lift platform. The FLRAA competition ultimately narrowed to two advanced concepts: the Tiltrotor Bell V-280 Valor and the coaxial rotor compound helicopter Sikorsky-Boeing Defiant X. Following an extensive evaluation process, the V-280 Valor was selected in December 2022 as the winning design, setting the foundation for what would become the MV-75 Cheyenne II. The design of the MV-75 Cheyenne II, derived from the Bell V-280 Valor, represents a deliberate engineering evolution of tiltrotor architecture focused on improving maintainability, survivability, and mission adaptability over earlier platforms such as the V-22. The configuration integrates aerodynamic efficiency, structural optimization, and advanced flight control systems into a cohesive assault aircraft design. At the core of the MV-75's design is its tiltrotor mechanism, which enables vertical takeoff and landing, VTOL, while also delivering efficient fixed-wing cruise performance. Unlike earlier tiltrotor configurations, the Cheyenne II adopts a fixed-engine, tilting rotor architecture in which the engines remain stationary on the wing, and only the protors and associated drive shafts rotate between vertical and horizontal positions during flight transitions. This architecture reduces mechanical complexity in the nacelles, improving reliability and easing maintenance compared to designs where the entire engine tilts. A cross-wing drive shaft connects both rotors, allowing single-engine operation in case of engine failure, an essential survivability feature in combat environments. The rotor system incorporates a swash plate-controlled variable pitch mechanism, enabling fine control authority during hover and transition phases. This enhances low-speed handling and precision maneuvering, critical for troop insertion and confined area operations. The MV-75 utilizes a V-tail configuration with rudder vaders, replacing traditional horizontal and vertical stabilizers. Flight control is managed by a triple redundant fly-by-wire system. A defining feature of the MV-75 is its extensive use of composite materials, particularly carbon fiber reinforced polymer, CFRP, across the wings, fuselage, and tail, combined with a single-piece wing construction that minimizes joints and reduces structural weight. The wing itself utilizes a honeycomb sandwich architecture with large cell carbon cores, which reduces part count, simplifies manufacturing, and significantly improves the strength-to-weight ratio. In addition, paste bonding techniques are employed in place of traditional mechanical fasteners, further lowering both weight and production costs. Collectively, these design choices result in a wing structure estimated to be roughly one-third less expensive than comparable tiltrotor designs, underscoring a strong emphasis on lifecycle affordability. The aircraft is optimized for high subsonic cruise performance, with a cruising speed of approximately 322 miles per hour, 518 kilometers per hour, and a maximum speed of around 345 miles per hour, 556 kilometers per hour, placing it well above the performance envelope of conventional rotorcraft. The platform will have a crew of 4 and is capable of transporting up to 14 troops. The design incorporates dual external cargo hooks, enabling the carriage of heavy underslung loads, such as artillery systems in the approximately 10,000-pound class, while maintaining high forward speeds of approximately 173 miles per hour, 278 kilometers per hour, a capability that significantly enhances operational flexibility for rapid battlefield logistics and deployment. The MV-75 is engineered around a modular open systems approach, featuring open architecture avionics and mission systems that enable rapid integration of new sensors, weapons, and communication suites, while minimizing lifecycle upgrade costs and operational downtime. The design also incorporates inherent scalability, supporting multiple variants including a utility transport configuration and a potential armed or attack derivative, such as the AV-280 concept, capable of deploying missiles, rockets, and unmanned aerial systems without rotor interference, as well as a medevac variant. The MV-75 Cheyenne II represents a fundamental departure from legacy tiltrotor evolution, constituting a system-level redesign intended to resolve persistent limitations in speed, range, survivability, and maintainability that have historically constrained vertical lift platforms. By integrating a fixed-engine tiltrotor architecture, advanced composite structures, and digital flight control systems, the aircraft achieves a substantial increase in operational reach while simultaneously reducing transit time, two factors that are critical for survivability and mission success in contested environments. Its ability to rapidly insert troops, reposition forces, or sustain forward elements across extended distances aligns closely with emerging concepts such as distributed maneuver and multi-domain operations, where tempo, unpredictability, and geographic dispersion are decisive advantages. Equally significant is the pace at which the program is advancing. The United States Army has deliberately accelerated development and procurement timelines, with initial operational capability now projected as early as 2027. This reflects a broader transformation in defense acquisition philosophy, moving away from traditionally protracted, sequential development cycles toward more iterative, risk-tolerant approaches that emphasize rapid prototyping, digital engineering, and early operational fielding. This acceleration is supported by parallelized testing and validation efforts already underway. At Redstone Arsenal and other test facilities, Army aviators and engineers are conducting rigorous evaluations of flight performance, handling qualities, survivability features, and maintainability metrics. These activities are complemented by extensive use of digital modeling and simulation, which allows engineers to refine design parameters and predict performance outcomes with greater speed and accuracy than traditional methods. This ensures that the MV-75 will not only enter service quickly, but remain adaptable as mission requirements and threat landscapes continue to evolve.